So, good afternoon again. I hope that all of you had a great energy break. Welcome back to the second DevOps session we have today, session 6.5, Software and Systems Engineering DevOps with a focus on model-based development. So my name is Peter Fromm, and I will be your chair of the session. First of all, very important, I think you all by now know the Slido tool, so please use it for questions because this is a little bit like the salt and soup. If we get your questions, we actually can grab that up and discuss them in the Q&A session, so please do use it. We're starting now with the first presentation of Bruno Chavez from the company Wind River, and he will have a talk on DevSecOps, Carves a path to digital transformation for autonomous embedded systems. Mr. Chavez, please.
Thank you for the introduction, Peter. Hi, so my name is Bruno Chavez. I'm a field applications engineer for Wind River UK for the aerospace and defense sector. Now, Wind River was founded in 1981 as an embedded tools and software company. We're about to reach our 40th anniversary, and the company has really evolved over time, starting off as mostly an embedded tools company and evolving into safety critical, DevSecOps, cloud, and cybersecurity. We support aerospace and defense, industrial, medical, and the automotive markets. So the world is evolving faster than we could ever envision. With this evolution came a need for faster feature delivery, faster bug fixing, faster software rollouts. Some companies have been pioneering this effort via DevSecOps and Agile. However, many players in the embedded world are still lagging behind. They are still using less flexible software development lifecycle methodologies. This is more prevalent in sectors that have safety certifications. And the purpose of this presentation, so it's to guide you for the market challenges that have brought about this change, as well as the best practices to adopt if you're trying to achieve a viable DevSecOps pipeline. So throughout this presentation, we will guide you through the driving forces and the real world requirements. We'll introduce you to the concept of DevSecOps. We'll explain it how we have adopted it internally, and we're going to share our experiences with you. We will show you some of our metrics, what we have achieved, and we'll end this with a case study to highlight the workflow in practice. So let's go on with the market challenges. Digital transformation. So some of us hear this term bandied about, but what does it mean? It is really just a way to say that all we do is digitized, like digitalizing your processes, the way you do things, from a paper trail to a digital trail. This trend started quite some time ago, a couple of decades ago. Digitalizing your work environment. So this is relatively new. It does mean containerizing your work environment and moving it to the cloud or accessing it through a VPN or containerizing an application. So a good example of this, containerizing an application, is Office 365. People working on it no longer need a fully fledged laptop. A tablet is sufficient, or a mobile phone, and the end user does not have to deal with updates or the availability on other operating systems. All it needs is a browser. Security is easier to implement since it's on a single source, as opposed to every end user's hardware. So this also makes it a lot easier for IT to manage. So you can say that in a way, we are going back to the centralized computer model from the old days where people had terminals connected to mainframes. It also means, give me a second. So it also means digitalizing your work environment. This is relatively, it means that digitalizing your end hardware via digital twins. While this is more relevant to people who are system developers who work in cybersecurity. It enables you to develop software before hardware is available. So for example, we've done some work on some CPUs which were not even physically available. So by the time the CPUs were available, all we had to do was rerun the tests and fix the bugs not seen in the digital twins. This accelerates development time exponentially As some of the teams still working on the boards and other things, and other teams, they're already doing testing on the software. And for cybersecurity, some companies do honeypot testing on digital twins. This is to entice hacker attacks, and the hacker has no awareness that he is on a simulated environment. So field connectivity or distributed cloud. This is the importance of networking devices to work as a hive or facilitate decision-making has been a focus of many industries. Whether it is a mine where multiple sensors are gathering data and making decisions on adjustments on support pillars or ventilation or whether to stop a drill. Or in a war theater where communication between the devices will enable faster defensive measures to be taken. So networking also enables the load balancing across these devices and distributed sensors. So you stop seeing this is a device X, Y, or Z. You are now seeing a network of capabilities and services. So in this picture, you can see multiple node connectors, like the fighter jets communicating amongst each other. And there's some other nodes on the ground. On the ground, they might use 5G. And on the air, they'll have to use some other radio transmissions. And what we mean by hard real time. So we mean determinism, which is associated with safety. And it means that task X runs at precisely time Y. This determinism is the difference between success and catastrophic failure. And this is where real-time operating systems come in to allow for this determinism to work. And if you're looking at, for example, the ODA, so what does this mean? It's the observe, orient, decide, act loop. This is an iterative four-step management approach that's used for decision or control making, and it's used in defense. It does have a business analog called the Plan, Do, Check, Act, which is used in businesses decisions or for product design. On the ODA loop, AI will now be able to assist this decision-making process by providing faster analysis of the data. So think of it as assisted decisions. We expect driverless cars in the future to use some form of ODA as a hive that functions perfectly, aware of its members' intent, and to facilitate driving, probably much more cooperatively than human drivers. And the risk management framework is standard to help secure information within systems. When you are developing such systems, you must develop them according to these secure norms, making them cybersecurity ready. This is based on some of the NIST standards, as you see here on the slide. And if you plan to develop for government entities, there will be some form of standard security requirements for your containers to be embedded in their systems. And airworthiness is a more complex challenge. It does require the safety component and hard real time. It also requires safety certifications, which are very stringent for obvious reasons. Introducing new methodologies and technologies further aggravates this challenge. How do you accelerate development? It's a balance between the we need new features versus the we need it to be safe. We don't want to crash. And autonomy. So the need for autonomous or semi-autonomous systems adds a new layer of complexity. This is all based on AI. If fully autonomous, does it operate in areas where it may cause damage to people, property, or itself? An autonomous vehicle that chauffeurs people around does not have the same safety requirements as an autonomous vacuum cleaner. You know, bumping into a wall is not the same as crashing into a building. And if it's optionally manned or semi-autonomous, then there must be some added safety requirements to protect the integrity of the operator. And then there's the need for these systems to be open and to also use open standards, which is a way to combat vendor lock-in and enables transparency and allows for security audits. So standards like SOSA for sensor interfaces or FACE for open avionics. And access to the source code makes it possible for safety certifications. You cannot achieve high levels of safety certification without having access to the source. Not having access to the source code also means that you're dependent on the vendor's success, the vendor's transparency, and a bankrupt vendor means a redesign of your product, which means excessive cost. and AI machine learning. AI is already here for fully autonomous systems and semi-autonomous systems that assist end users. But what does this really mean? So it's a combination of techniques like decision trees, rules, hard-coded logic, and machine learning. And machine learning at the edge can be achieved in two ways. So machine learning on the edge target, which is computationally expensive and power hungry. So it requires large processors and battery storage. And you can do something simpler, which is cloud-assisted machine learning. This means offloading the machine learning capabilities to the cloud. The device essentially performs two functions, like data gathering, maybe pre-processing and then uploading it to the cloud, or lean machine learning model implementation. So you have a lean model that works on lower end processors. And then every time a new model is generated, it's downloaded and implemented. And there's also AI at the development side. So this means the gathering of analytics to facilitate the development and deployment processes. So which type of cloud do you have for business agility? You have an operational cloud where you're providing commercial services. You have a need to maintain certain levels of service and proper resource management. Or do you have a tactical cloud for defense, where each device needs to be part of a mesh devices that form a localized, distributed, independent cloud? So this is a part of the deployment model or the business model at the end. And then there's the maintenance of such systems. How do you deploy the software? Are you using OTA, containers? Are you deploying manually via flashing? Does the device come to your storage, to your facilities for flashing? Can you improve the delivery? And we also see the need to reduce development time from months to weeks or days. This is achieved through the adoption of agile methodologies into technical practices, like DevSecOps. Lowering QA times is also important because this tends to be one of the major bottlenecks of development, testing. And for companies working with or for federal organizations, they must follow the continuous authority to operate process. This is CATO. That means that the owner of such system must develop, certify, and maintain said system with appropriate security controls. And this is far easier to implement if you're using containers. So these challenges are what are driving the market needs to turn to faster methodologies. So these are methodologies like DevSecOps. The moving to DevSecOps was an operational requirement born out of the DoD's need to evolve into an agile methodology for development with added security. The DoD was a late adopter of agile. After adopting waterfall and other methodologies, it still made it hard to coordinate contractors. It caused integration issues with artifacts from several sources, and then inevitably caused delays in deployment. To mitigate this, they've developed their DevSecOps methodology, which is based on the software factory concept, which is essentially a modular system containing multiple pipelines, each having their set of tools, processes, workflows, and environments. This allows for the production of deployable software artifacts with minimal human intervention, as most of the process is automated. So you can see on the slide on the left, this is an example of the software factory. This is actually taken from the DoD website. There are 3 pipelines, each of them with a specific development environment, test environment, and then they feed ultimately to an integration environment and produce a final artifact that goes into a released artifact repository. Now, an artifact is a consumable piece of software produced. It can be a binary, a container image, a jar file, a script, a scan result, a test result, anything. So it's the output of any of these stages that can be considered an artifact. And security is automatically a part of every phase of development. A secure and auditable pipeline from the code development to the final target deployment. And on the right side, this is the high-level concept of what Wind River has created following the DoD software factory. So this is what we'll explain better in the following slide. This is how we containerized our workflow. It's done using cloud-native applications, which are decoupled. So the hardware, platform, software application, they're independent from each other. They're scalable. So because it's in the cloud, you can leverage, you can give more memory to this container. You can give it more CPU usage, which makes it flexible. It's also easy to be changed and or upgraded. You can match also the services to be orchestrated to match the available resources, or SLAs. And it's automated. From the moment it enters one stage, it will go all the way through the end unless it fails, which is, obviously something for the developers to fix, which is part of the CI/CD cycle. And so this is DevOps using the modern CI/CD methods. So each of these containers, if you're looking at the RTOS repo or Linux repo, third-party repo like bare metal, then it will go onto the developer repo, and the developer repo will then go to do some scans. So it could be coverity, it could be some static analysis, some license analysis, whether you're performing according to GPL or not. And then it goes, to some forensic, so passing the forensic repos, and it will then go into the build server to test for the build. After building, then it goes on to creating some evidence if you got some safety requirements. So it goes to safety image generation, and it goes on to a test environment as well. For example, you can see Kimu there, or Symix, or some other products. There'll be or it can actually be the end target as well. So you could also have some of these elements which are linked to real hardware targets. An example would be secure authentication is performed then between each of the nodes. Let's say you start off with a MATLAB node to a C converter node. Then it will do some static analysis. Then it will go to the compiler node. And then it goes to the test node. And at every stage, the artifacts are stored to ensure reproducibility and auditing. So an example here. Developer's at his desk. He's just writing away some code. He uploads this code to the server in the cloud. This cloud server, which has the DevSecOps pipeline, has multiple containers, each of them for a specific purpose. So this predefined pipeline takes the code throughout the several stages and outputs a final target. It could be a binary, pseudocode, new code. This then goes to a deployment server that has communications with the final target and updates the final target with the new artifacts. So in case of the binary, for example, this server now gathers data from the final target, which could be sensor data, monitoring data, logs, etc., and pushes it back up to the developers. So this is to monitor what's happening over the time. You'll notice here that, for example, this end target is a hypervisor. This is a recommended approach for future development, regardless of what you're doing, because you want to separate some functionality which might be safety critical, if you do have those requirements, from other non-safety critical functionality. So this RTOS, which enforces safety critical functionality, probably doesn't need to be updated, or it needs to be updated rarely. But you can do new updates to add functionality to Linux or to a third-party operating system, because these are now just virtual machines running on top of the hypervisor. It makes it easier to segment your design. And this is something that should be considered initially at the first stages of the design of your projects. So let us give you some overview of our experience when we've implemented DevSecOps. So the following figures I've taken from one of our products. This is VxWorks. This is our RTOS. So we have 66,000 tests running overnight. These are integrated into our test suite. Almost 100% of the test areas are automated. And all these tests are running every night. At the end of this, by the time we release code to our customers, it's no build issues, no coverity warnings. So this is very high quality code. And all this, we run it some nightly, some weekly. And the key to achieving these metrics is automation. And so having an automated pipeline from the desk to the end target. And with significant automation, you attain significant growth in the coverage. So this results in always working software. And notice that the pass rates increase everywhere from 85, back in 2016, I think, to about 99% holding. So if you look for, these are all VxWorks metrics. So if you look throughout the bottom of the releases, we have very high test coverage. And then there's also the release coverage. It increased significantly. Back in 2000, well, when we introduced SR 600 or 600, we switched to the LLVM compiler toolchain, and we had to write new tests for it. We also made sure that every component and feature were above the 90% percentile. So this is why we had this dip. And then after adding it, just the release coverage continues increasing. And the technical support requests have been dropping as a result of this. We had less issues, less problems, less cases to deal with. So notice the test summary report decline over time. And this is at the same time that we're increasing our added features per release. And we're just talking single product. We're not talking of all the other products we have. So all of this is achieved in a single product, but we achieve this throughout the other products as well. And now let's look at the staggering amount of test cases and target coverage that we achieved on our overnight testing. So 66,000 cases, as we said before. And none of this would be possible if we didn't have digital twins. We're running 9 BSPs, 288 targets. And this is all done in a digital environment. This allowed us to reduce our lab space enormously. Our power consumption as well, because we don't have racks of machines, is also reduced. And also, you also achieve acceleration by offloading this to the cloud. So none of this will be possible at this level if we were just using standard hardware. Well, it would be possible. It would be much more time, power consuming, more expensive. So the key element to achieve this is simulation in digital twins. And this is why companies must adopt a digital twin strategy, or at least start planning for it. So regardless of the sector, if you're producing software that runs in a device and or communicate with other devices, the key component to cut down the time to market is a digital representation of the end targets. And a digital twin can be anything. Machinists, you can do digital twins for chemists when you're doing a hypervisor. Image is basically a digital twin, but it can also be a CPU simulation that's running on multiple racks, or it can be you're simulating a board, or a network of machines communicating between each other. So feel free also to view one of our past seminars on digital twins. So there's a link attached. You can pick it up later from the notes. And this is some examples of digital twins. So wind turbine simulation. This is very important, especially because these are very expensive devices, and when they fail, it's very expensive. So telemetry data, so you gather the data from the blade designs and the rotor models. You have a lot of sensors on these things. And you're gathering the data from the sensors, you're pushing it back up to the digital model to see how it performs. If there are failures, you can also do root cause analysis. You can do a lot more simulation to do stress analysis, and you can increase or improve your design over time. The other thing, which is probably more interesting to some of you, is Formula One car simulation. Now, these cars have a lot of parts, and it's all about time management. So, and this is mostly about fine-tuning injection to the motor. So it's all about managing which ports, are open. If you're opening the fuel port, how many milliseconds, opening the air port, opening the exhaust port, how much do you route from the back of the engine, of the exhaust back into the engine? What's the cornering ability? What's the reaction times between the steering? And all this data is pushed up from the physical car through all these sensors, and it's pushed back up to the digital twin. And then new algorithms are developed based on this. And then they're pushed onto the IC to DCU and others to other components of the car that allow for the better driving. Which takes us to the feedback loops at the edge. Most of you are familiar with the several stages of development. So you have plan, develop, build, test, release and deliver, and up to deploy. The emerging requirement now is the last two stages of a DevSecOps pipeline, which is operations and monitoring. Continuous operations and monitoring also allows you to provide extra services to your end customers and create revenue streams, new ones. So these last stages will be provided via cloud services and enhanced by the use of analytics. This is the gathering of the data, telemetry, and then monitoring the data, optimizing it, going through the initial code back up to the end. So this is where it all comes through. This is all about the loop, as we've been discussing. And this is all about telemetry, and it's all about the data. So you have this data has to be constantly fed when possible. If it's a disconnected device, you gather it at the end, but you must constantly gather data. And then you can use the AI to extract new functions from this data. Then you model these new functions on a digital twin. Then you push them to a test hardware. You check them. It goes back to the digital twin until you performed what you want to do with it. And when you're ready, you can then push whatever you develop, whether it be a new machine learning model or some new algorithms. You just push them to the edge devices, and you continue this feedback loop. You can, and with this, you always enable new functionality and constant refinements. So let's go for the case study. This is a case study from automotive. It doesn't have to be exclusively automotive. There are analogs to this in every industry. So let's say that you're a car company. You use some customer relationship management software to sell new cars with the autopilot.
Just a short note, you have 2 more minutes, please.
Yeah. So, and this gathers data from social media. These users are complaining, oh, the car's failing, oh no. So you pick up this data to gather the usage data from the car sensor suits. The data is confirming that the drivers are constantly overriding the autopilots during the sharp cornering because they're afraid. So the car company develops new algorithms to adopt to modulate the speed during curves. Cars are updated over the year to include the new functionality. And this usage data is then further tracked to optimize the autopilot for new and existing cars. And the cycle thus continues. And this is why the embedded world must really embrace DevSecOps. You must embrace containers. You must optimize your workflows to this new digital world. You must also consider security at every stage of your development and consider offloading some of the processing upstream to the cloud and other to be enabled on the edge devices, and consider AI in your future devices. So with this, I conclude my presentation, and I thank you all for listening.
Yeah, thank you very much, Mr. Chavez, for really a very interesting and good demonstration of how DevOps actually can work. I found it very impressive, especially when you said about the 66,000 test cases you have and the digital twin. So we might maybe catch up on that a bit also during the Q&A session to also get some experience on how you did it and what kind of efforts went into that. Mm-hmm. So we are now coming to the next presentation in a few seconds. So please stay tuned, and please, from the audience perspective, do use the Slido to also bring in your own questions. Thank you very much.
Thank you, Peter.